Thank you very much for the invitation here to speak today. And when this came several weeks ago, I found myself thinking a lot about what I should say and practicing at every opportunity to find an audience. And the cows really liked it when I moved away from the microphone, so I'm not sure what's going to happen today. Even though my name is on the talk and on the program, I work with a group of forest soil scientists within the BC ministry, and some of these people have since retired. But many of the publications that I'll be referring to are in fact joint publications, and I should acknowledge all my cooperators and people that I've learned from quite a bit over the years. And the way I'm going to structure this talk, I'm going to talk very specifically about one experiment that I've been involved with for approaching 25 years now, and then towards the end of the time, how we can use some of that information and some of those approaches on more landscape level questions regarding soil conservation. In the world of forest soil, some of the very early questions were what happens when organic matter, for example, is removed from forest ecosystems? Does that result in a productivity decline? In the 1980s and 1990s, there was a great resurgence across many jurisdictions about this idea: what are the implications of our forest practices on the future productivity of these forest sites? So from Idaho, British Columbia, Ontario, people looked at these questions, and I'll be talking very specifically about British Columbia today, and these are translated into a variety of forest soil conservation guidelines. So in a common forest setting in this part of the world, what you'll have is a road being developed, and again, soil stripped, heavily compacted while it's used for traffic. And then there's an area adjacent to that road where the trees are brought by a skidder, and then a piece of equipment, a processor, cuts out defects, trims off branches, sets them up, and then another piece of equipment usually then loads from that area onto the truck. So in that area close to the road, you get repeated machine traffic and a number of different things happening, and some of the final steps are piling up of that woody debris. So a lot of machinery moving under different conditions several times, and then that larger area would simply be the traffic of harvesting and transporting the logs to wherever they're processed. In the particular case of Aspen then, what we can see when we go back to these sites, these roadside processing areas often stand out quite distinctly as areas with really poor or low quality aspen regeneration. And when we go with company foresters to visit these sites in the summertime, we can see the outcome. There's plants growing there, but they're not the plants that we necessarily want. And we can see changes in soil structure. So this very coarse platey structure is a common feature where there's been repeated machine traffic over the site. And then the question comes, well, you can show me these things, but what difference is it going to make 60, 80, 100 years from now when we try to grow another crop of trees? And the long-term soil productivity study, which is an international study which initiated with soil scientists and the U.S. Forest Service, has 56 sites, and it's meant to address exactly that thing. What are the consequences of some of the things that we do on forest sites in terms of their long-term productivity? The power of this large international study is that we're all using the same study design. So there's 3 levels. I'm sorry, I'll backtrack a little bit. So the initial work from the people who designed this study was that when they looked in the literature, the 2 main factors that could be documented to result in a decline in forest productivity were removal of organic matter, or else a change in soil structure, a negative change in soil structure, compaction, loss of aeration, porosity. So the study is designed with these 2 principal factors, and you have 3 levels of organic matter removal. So from only harvesting the bole, the absolute minimum, leaving the fine branches and so on the site, and the most extreme treatment, you're taking all of the woody material off of the site, plus you're stripping of the forest floor. So comparable to what happens on a road or even some of these roadside processing areas. The levels of soil compaction, so no compaction, and we went to great efforts during the harvesting to have the minimum amount of equipment movement on the site during harvesting. And then we came back and, as you'll see, deliberately compacted to a consistent level to the best of our abilities with equipment and people. So every possible combination gives you 9 possible treatments, and then on a study site we replicate this 3 times. So there's 27 plots in one of these sites where we've got all of these combinations replicated. The site that we used just across the border in British Columbia was a very productive aspen stand. So it was a mature stand, about 100 years old, and the typical type of understory vegetation. In terms of soil properties, it had about a 7-centimeter organic horizon, and it was a glacial-fluvial veneer. So the history then, this upper lighter layer was a secondary deposition and was a fine sandy loam to silt loam material, 20 to 30 centimeters deep and stone free, and then a clay loam material below it. So common to many soils in this part of the world, that will impede drainage when you've got precipitation events, big events, and so on, and there's a degree of mottling in the site, but it's a very highly productive site. To do this work, so 27 plots in total, which are in this image in the center here, but we had to do it over 3 sequences, sort of 9 plots at a go, and so it's spread over 5 years to actually establish this study site, and within it, and then we combined some operational harvesting, are the 27 replicate plots. Each of those plots, 40 meters by 70 meters, we split in half because we're interested in both aspen and white spruce. So half was planted a white spruce, and where we planted the white spruce, we did a manual brushing treatment every year for the first 5 years. So the idea being that the growth of that tree would reflect the soil conditions, not the plant community around it or the possible effects of competition. On the aspen side, we essentially left things and we get a natural development of whatever was there after our various treatments. The 2 treatments, the compaction and the organic matter removal, when we do the statistics, there's not an interaction term, so I'm going to talk about them separately. And this is what we did. On the head of an excavator, we got a large compacting head. Our 2 levels of compaction was to try and get a 2-centimeter depression in the mineral soil or a 5-centimeter depression in the mineral soil. And then the excavator operator would then carefully go over the entire plot trying to create this kind of compaction. When we look at the upper mineral soil, 0 to 10 centimeters of bulk density, that's the pre-harvest. So at the treatments, when we aggregate things and express them as means, there was no significant difference, which is exactly what we wanted. And again, we had a wonderful uniform study site. The year after treatment, when we come and measure, we did achieve a treatment effect. So there is a significant difference where there is no compaction, C0, versus the 2 compaction treatments, but no difference between those 2 compaction in the upper mineral soil bulk density, even though we were trying to create something. And when we come out to years 5 and 10, the compaction 0 is very comparable to what it was under the mature forest stand, and we still have elevated levels of mineral soil bulk density in those treatments. And I've currently analyzing year 15, so I'm going to jump around. Sometimes we'll talk about year 10, sometimes I'll talk about year 15, so please bear with me. For the height of aspen regeneration from these compaction treatments, by year 4, there is a significant difference in aspen height for the no compaction versus the 2 levels of compaction, and no real difference, whether we called it the light or moderate compaction and the heavy compaction. It didn't show up as a difference, and that pattern, that relationship has continued through to year 15. On the white spruce side, a similar type of picture in that compaction 1 and 2, there was no difference, so when we pool those 2 and compare them with compaction 0, we got those kinds of significant differences. And those, again, started in about year 4 and have continued on through year 15. Give you a visual impression at about year 10. So C2, that's the acronym then for the heavy compaction treatment. And one of the interesting things when you compare it back to that initial slide that I showed operationally, so in our research applied treatment, we didn't get a significant difference in the amount of aspen regeneration with compaction. So what happens on operational sites where we get no or very poor aspen regeneration is even more than what we created in this experimental site, more disturbance. And if you compare it with C0, then you've got a plant community that reflects where we've planted spruce, and there's a degree of aspen growing there, very similar to what harvest, everything being done properly, should look like. Organic matter removal treatments, again with an excavator with a great big bucket, and stripping off the organic material, the forest floor around after harvesting, the May period immediately after harvesting. We didn't want to pull the stumps and create that kind of additional disturbance. And then in an aspen stand, you've got that dense network of lateral aspen roots. So that bucket would ride along those roots and scrape off the organic material, and then gradually move it off some distance from the plot. So what we ended up with was about 50% of the plot would have exposed mineral soil, and the other 50% would have a very thin, say ½ a centimeter or less of organic material left behind, because we wanted to retain that root system. We weren't trying to uproot the aspen, but still a real decrease from 7 centimeters to ½ a centimeter or less. The upper mineral soil bulk density, so again, no difference in the pre-harvest, and the movement of the excavator and the scraping of the action of that bucket created a degree of compaction here in the organic matter removal treatments. The other treatments where organic matter was retained, again by year 15, it's very similar to what we had pre-harvest. Aspen height by organic matter removal, even by year 2, we had a significant difference, and it was a gee whiz difference. Where you strip the organic matter was clearly less than where the organic matter was retained. And both of these treatments in an aspen stand, it didn't really amount to much. When we leave the tops on an aspen stand, it's only about 50 cubic meters per hectare of woody material, and that's a very small number compared to coarse woody debris and forest floor, which is in like the thousands of cubic meters per hectare. So it was a very slight difference in those two treatments and what was actually on the ground. Aspen density and the removal of forest floor is a real stimulation of aspen suckering. So from those lateral roots, warming will increase the amount of suckering. So when they're fully exposed to light and the insulating effect of that forest floor is removed, that stimulates. And then to a degree, the scraping action, the slight wounding and severing fragments of the aspen stimulates suckering. So in the first few years, there were significant differences, but again, by year 5, they're depending on the carbohydrate system and to maintain all of those early suckers, and there was a rapid mortality, and by year 5 there wasn't much of a difference in terms of numbers of aspen stems between the OM3 and where we retained organic matter. For spruce height, it took a little bit longer, but by year 5 we were getting a clear separation. Again, the OM3 is just not a good place to be a tree, and that situation has stayed the same through to year 15. How do these look? This is a year 20 picture, one of the older replicate plots. And one of the things I want to draw your attention to, there's a lot of green things there, but it's dominated by willows. So that exposed mineral soil stayed as a receptive seed bed for several years, and willows, and to a lesser extent balsam poplar, seeded in quite dramatically on those sites, and so they dominate the woody and the shrub components of those systems. And that's a very different amount of shrub cover compared to where the forest floor was retained. So the understory plant community, the relative cover of the shrub community, is very similar by year 20 to what we had under the mature aspen forest that was 100 years old. Trying to put those two effects together, so in terms of spruce height, that front rank shows the heights at 10 years, so a very clear difference where organic matter was retained versus where it was disturbed, and not any significant difference in terms of the levels of compaction. Where you did retain the organic matter, no compaction was clearly better than where you had compaction effects, but there's a fair bit of variability in there. Expressing it another way, looking at the at year 10, the heights of the spruce trees versus the upper mineral soil bulk density, we got a pretty good relationship with that, and a clear trend. For aspen, again, the similar idea where the organic matter was removed, the heights are dramatically less. The level of compaction after that didn't make any difference. Where you've retained organic matter and not had any compaction, that's the best height growth. And then there's a clear drop off when you get to either level of compaction that we had in the experiment. And an even better R-squared relationship here, showing that aspen is more sensitive to these changes in the upper mineral soil bulk density than the spruce was. The question that the operational foresters give us, what difference is that going to make? So at year 15, we can interpret a site index, which is a standard forestry measure of how productive a site will be. The higher is the site index, the more productive a site is for a given tree species. So for aspen that we're harvesting in the Dawson Creek area, as a broad average, 17 or 18 would be the type of site index that we'd have. So if you look at the effects of organic matter, retaining the organic matter, we've got better than average aspen stands growing here. Where we've removed the organic matter, we've dropped to a level where it wouldn't be considered a merchantable aspen stand into the future. So we're not harvesting currently anything less than about a site index of 14. So we've dropped right off the scale with the OM3 based on year 15 growth. Where we look at the compaction effects alone, so no compaction, site index of 19, again slightly better than average aspen site for our part of the world, and we've had a clear drop in the productivity. But if you look at those heights, and from doing this all my life, walking in forests, to consistently judge the difference of 1 meter between treatments, it isn't a big difference. And it's only when we do this kind of replicated experiment and detailed measurement that we can document this kind of thing and show a significant difference between the way we've treated a given site. So in summary, the 10-year results from this study is that forest floor removal was the most disruptive influence, and it's had a legacy to the 15-year mark. For both aspen and spruce, that soil compaction was a clear negative effect. And the importance of this idea is that where we've had a failure of aspen regeneration, the common response is, well, we'll just plant spruce. And that can meet your legal obligation, but the point that I like to make based on the results of this study is that it's still not a great place to put a spruce tree. You've fundamentally changed the productivity of that site, so you might be meeting your legal obligation. You have left a legacy of a decrease in the future productivity of the site. You've got an aspen failure. That upper mineral soil bulk density was the best single variable of the variety of things that we looked at for both spruce and aspen height growth. To a degree, and you could see it in some of the graphs, I didn't draw it to your attention, in that very uppermost layer there's a gradual buildup of organic material, biological activity, and so again, similar to some of the earlier talks with organic matter and increased biological activity, you get some benefit in soil conditions, and we're seeing some of that happen to a certain layer. But our upper mineral soil bulk density was still in a range where we have reduced plant growth rates to be expected, and that comes from taking these soils, and it's a civil engineering test, a Proctor test, where you compact a soil as much as you possibly can, and it's suitable for determining road bed suitability and so on. And these soils, 10 years after the fact, 80% was the result from some of these greenhouse studies and plot trials, where you've got a clear negative effect for a variety of tree species. And 10 years after the fact, that upper mineral soil was still at 86% of its Proctor value. So in the range where it was not a good place to be a tree into the future. So a study like this, a detailed study like this, then gives us value for when we're going out on a site immediately after harvest and looking at those visual indicators and trying to judge whether this is an acceptable condition or whether this has implications for us into the future. So with more confidence, when we see that coarse, cloddy structure and the undisturbed portions of the site have, in this case, almost like a fine granular soil structure, we have a basis of evidence to say whether we're making a change. How then do we apply some of these things? So since the late 1980s, people have been working on various techniques on how to efficiently and effectively survey a site after harvesting. And one of the recent techniques that we're using, this is from 2013, is using GPS technology and some of the things that are available to us now. So that blue outline then is a potential harvest block. You can use a utility in most GPS programs to then randomly assign a whole series of points. And then with a completely random design, you can efficiently walk over the site and sample 100, 120, 200 points, whatever is suitable for your confidence limits. So in this particular example, which is an operational example, and the purple boundaries are the actual cut block, and just the aerial image that we imposed it on, harvesting was actually partially underway. So when we actually did this work, harvesting had been completed, but our working copy image showed harvest only partially underway. So essentially then we do a walk through the site, and one of the key things that we look at are soil textures, our classes of how much disturbance is acceptable is based on soil texture and coarse fragment content. So in say a loamy textured soil, up to 10% disturbance would be an acceptable outcome. If you've got something like a silty clay loam, 5 centimeters or more in the upper 30 centimeters of the mineral soil, that would be considered as a high compaction hazard where there would be negative consequences. So we do that walkthrough, we can document the particular locations where we assess this soil, and then we can also document photographically what we find in different portions of this, and then randomly assign the points and do an evaluation. And the great value of this is that with the confidence intervals and that lower confidence limit, if the limit is 10%, as in this case we came up with 35% disturbance with the lower confidence limit, then clearly you have exceeded what was considered as the maximum limit for soil disturbance on this site. So the red dots are the ones that had a negative soil disturbance category where we sampled it, and the green ones where there was no visible sign of a negative disturbance. Another example of how we're using this approach, and again some modern technology, again 10 years after the fact, what difference does it make? Divided an area near Dawson Creek into 10 kilometer squared sampling cells, and ones where more than 20% of the merchantable forest have been harvested in the last 20 years. We then looked at cut blocks that were older than 10 years and randomly selected some of them to look at. And this is an example of one. And then what we were testing is the use of drones. So we had a local contractor with a fixed wing drone, and he took a series of high quality digital images and near infrared images and combined them to give us a detailed look at the plant community that was coming back on the site. And this isn't the high quality image. You can't, there's so much memory you can't put them into a PowerPoint and show them up. But the idea is that you get a high quality image, and then you can differentiate out features like this and former roads and the areas around them with a high degree of accuracy. And then we went on site and did a little bit of reconnaissance, ground truthing what we found. So I'm standing on the former road. You can see some woody debris that's been burnt. And then I'm looking across the roadside processing area, and that's the area where only harvesting took place. So, and this is I think 12-year-old aspen stand, 12 years post-harvest when we were in there. So giving us ground truthing to help us with those images. And one of the things that come out in doing this, the dark blue at the base of these columns, that's trembling aspen. And the site was dominated by trembling aspen, 80% or more, and so that's what you'd expect and that's what you want to have in terms of the forestry world for regeneration. And so for a 10-year-old aspen stand having more than 20,000 stems per hectare, that's a warm, comfortable place to be a forester. You like to see that. You have confidence that there's going to be an aspen stand in the future. You had a little bit of aspen, so about in the order of 2,000 stems per hectare on both the road and the roadside processing area. This orange reddish tone are balsam poplar, which again have seeded in. So you've got exposed mineral soil, and back to the long-term soil productivity site, that mineral soil has been a receptive seed bed, and so you've got another species, balsam poplar, seeding in. There's a small amount of balsam poplar that originated from rootstocks in the harvest-only area, and then that yellow is white spruce. So if you just look at these numbers, you think, well, maybe that's not so bad. You've got a species shift, but aspen and balsam poplar are broadleaf species, but that's only the number. If you again think back to that image, their rate of growth, their distribution, it's not likely to be a commercial forest stand into the future. So we have dramatically changed these areas into the future in terms of what they're going to provide for a potential for a future forest crop. And that idea of a species shift and an easy visual change, so this is in Fort Nelson, where I also have worked over the years. So here's a 15-year-old aspen stand, and just quick visually, you've got that grayish tone reflecting off the aspen bark at this time of year. Another aspen stand harvested at a similar time, and you get a very patchy appearance and a lot of this reddish brown tone, which is dominated by paper birch, which again, when we go on the ground and investigate, has seeded in. So it was dominantly an aspen stand. During harvest there was disturbance, and the regeneration has a significant component of paper birch. So a very different condition than even a natural disturbance on those sites. Another example of how you can evaluate your success that I've been involved with the soil scientists that I described earlier is under our legislation in British Columbia, we have a monitoring protocol. Have you achieved the soil conservation objectives for the province? And you look like things like coarse woody debris, the amount of disturbance, the amount of road, are the roads hazards for erosion and so on after harvesting when everything is put to bed. So we got funding, and this is 124 recently harvested sites all across the province. So this was a random selection trying to get a distribution. These weren't problem sites or sites where people had gone to do investigations. This was an intentionally completely random harvested within the last couple of years, and then we sent a fixed-wing aircraft and got very high quality digital images and all the proper things to properly display that image. And then the soil scientists that I worked with, we sat in our offices and we all looked at that image at the same time by shared computer screens. So the effect was, and again, this isn't the high quality image that we worked with, but you had down to 5 centimeter resolution. So you could judge the sizes of coarse woody debris that were on the block. And with one person guiding us and shared computer screens, it would be like being in a helicopter and flying over the road system and over the block at a low elevation. And it had the great benefit that nobody got nauseous or airsick when we were doing this, as can often happen in low elevation helicopter flights. And then we would all evaluate, and in 10 minutes we could all look at the same block and come up with, for the 6 criteria that we had, how successful was this example in evaluating, in achieving the objectives that the province has. And one of the things that we found out of this sample of over 120 blocks over the province was that, depending on which factors you looked at, but on average about 18% of the blocks did not achieve what the province had set as the expected outcomes for soil conservation. after harvesting. And consistently, one of the areas where we found the most concern from that visual inspection were those roadside work areas. And what often happens in those roadside work areas in operational conditions is that people are sensitive when you get rainfall events or poor conditions. So the trucks don't come to haul because the roads are bad. The skidders don't operate because they might create ruts out on the site. But you can still use a big tracked machine to walk up and down next to the road and process the logs and do some work. And so I think it's that sort of mental adjustment. You can still get by without thinking of the consequences of what's happening to the site, which is supposed to be growing trees into the future. There's a higher amount of disturbance allowed because we know equipment has to operate there, but that area is still expected to grow trees into the future, whereas the former roadbed usually is not. Going back then to the group of 5 or more people looking at the same site at the same time, this process is called expert elicitation, and it's used in a wide variety of questions where you get a group of people together and quickly do they say this is okay, this is maybe okay, this is definitely not okay. And in our case then for most of the time, this green, it's 80 blocks, but say 4 out of 5 of us at a minimum came to the agreement that that is a certain condition in terms of the scale that we were looking at. There was a high level of agreement. There was a certain number where it was a bit more of a spread, but that's still, 3 out of 5 people called it the same way, and only a small minority, 10 out of 124 blocks, where we were much more scattered and didn't have a consensus at the end of an independent vote. So what this technique offers then is that a large sample, 124 blocks, consistently evaluated, and you have some confidence that the outputs that you get give you something to evaluate. Have you achieved what you were hoping to achieve? Yeah, so sorry, that's end result. Are things looking the way after harvest that you would expect them to look? A related study that's underway this year, again focusing on those road systems, so similar to this part of the world, there's permanent road systems through forested land areas, and they're often used both by forest harvesting and oil and gas industry. But then when we focus on strictly areas that are harvested, there's a system of roads that only have a use for the time period that you're harvesting. So how much are those areas? They're the most heavily impacted, the greatest loss for the long term to productive forest sites. And by using, again, a variety of GIS and high quality imaging, we're doing a province-wide sample of these sites. And one of the questions we want to look at, for example, is how has the amount of road changed over time? So 20 years ago, when we look at older cut blocks, what's the relative area in roads as a percentage of these blocks compared to what we're seeing today? All of this information and so on has often been combined into these guides for people, but I guess the point that I want to make is that we have these tools, but often in the operating world, when you go out to operational logging sites, there's always new people on a crew, whether it's the foresters or whether it's the equipment operators. So there's a constant need to extend and make people aware of the information that is available and has been available for a long period of time. Probably preaching to the converted, but the value of the long-term studies like the LTSP site to provide us with that data for relative confidence of what we're seeing, what implication does it have into the future, and then a monitoring component. Are our practices on the ground doing what we hope they should be doing, and can we do it can we monitor in a meaningful and effective manner? So again, this long-term soil productivity study, there was the soil scientists, army of summer students over the years, and a number of graduate students. For example, some of Scott Chang's graduate students did work on this LTSP site over the years, and so these ideas that I'm presenting are a compendium of many people's work, and probably if there's one idea that you liked in this presentation, it came from somebody else.